So we're going to start this session with Faulkner. We'll talk about vacuum asymptotic.
Great. Can you hear me? Okay, yeah. So I'm going to talk about some work that I did more than a year ago with my student Min Lee. And I'll also touch on some work that I did a couple of years ago. And then I'll mention some work that's to appear. So the one sentence summary for this talk is quantum error correction and von Neumann algebras. But let's just get started. Okay, it's not working. Yeah, there's always that. Okay, great. Now it's working. Okay, so let me start by reviewing quantum error correction in ADS CFT and how we sort of understand it in like the simplest possible example. I missed a slide. So in ADS CFT, we think of gravity as emerging from quantum mechanics. Aspects of this emergence are captured by quantum error correcting codes. And one way to build a code is to think about some simple state like vacuum ADS. Start acting with operators, say bulk operators that you can reconstruct in some global way using, say, HKLL or something. And then act with a finite number of those. You generate a finite dimensional Hilbert space. And then you think of that Hilbert space as living inside your physical Hilbert space, which is the CFT Hilbert space, the boundary Hilbert space. So I'll interchangeably use code and bulk and physical and boundary. This encoding map should be an isometry. And the way to characterize the quantum the quantum error correction properties of this code is via the following useful theorem. So in particular, if I imagine the bulk Hilbert space factorizes, it's a finite dimensional, so it potentially factorizes like this as a product of two Hilbert spaces associated to two bulk regions. In this case, they're going to be the entanglement wedge and the complement entanglement wedge. And imagine.
Get lunch first. Yeah.
Right, and so what does it mean to reconstruct the bulk region? Well, imagine I have a bulk operator in the region A, call it phi A. If I can find a representative of that bulk operator, call it beta of phi A, that acts purely on the boundary and only in this Hilbert space associated to boundary region A as such, and it acts on that boundary region as it should act in the code subspace, then that's what we call an operator reconstruction. It turns out that that condition, if we can do that for all possible operators in this region A, is equivalent to another condition, which is called the Néel-Laflamme condition, which is the simple statement that if I take the errors, where the errors in this error correcting code are related to sort of tracing out the whole boundary region A complement, if I take errors, which now is just any operator in A complement, this XA, and I project it to the code subspace using V, then it will commute with this operator phi, any operator phi A. Okay, so these two conditions are equivalent, and it's a somewhat non-trivial theorem to prove that they're equivalent, but it's something that is sort of going to give us lots of important properties of this error correcting code. Okay, so that's great. So some comments. This sort of operator reconstruction language that I'm using is sort of a Heisenberg picture version of reconstruction where we try to map operators. So beta here is a unital completely positive map. And it's useful to use this language, especially when I'm going to talk about algebras. There's a complementary situation that arises here. There's no seeming difference between the region A and A complement. Where remember, sorry, I should have said this region, of course, is delineated by the RT surface. So I can also do operator reconstruction in the complement region. And if I have both of those conditions in this theorem, so I have two versions of this theorem. One where I have condition 1 and 1 prime, where 1 prime is just operator reconstruction for the complement region. Then if I have that, and in fact, it's if and only if, the relative entropies agree. So the boundary relative entropies agree with the bulk relative entropies. Okay, so then that means, if we know something about the relative entropies, then we can find where the operator reconstruction works, and that's how you prove that it's the entanglement wedge that works. Okay, so in this setting, we expect that that this error correcting code is only approximate in nature. So what you might mean by that is that v dagger v is maybe not even an isometry, but as an operator in the operator norm, it's close to the identity. V dagger v is close to the identity, and again in the operator norm, this reconstructed operator approximately works. Now there are some shortcomings. There's of course a huge ambiguity in how we pick this small finite dimensional Hilbert space. There's many choices. The things that we're using, these single trace fields, if I'm imagining my boundary CFT is at finite but large n, they don't form an algebra. So at some point I'll act with them and I'll start creating a black hole or something like that, or there's some just back reaction will also do it. So usually you deal with this by truncating the Hilbert space with projections. But when you do that, you might worry that you lose sort of notions of bulk locality. We're missing other aspects of effective quantum field theory, like causality, locality, energy conditions. So I'd like to build those in. And finally, there's this question of sub-ADS locality. The code that I constructed for you in the beginning is, really only relied on large n, so I could have equally done it in a very stringy setting. So does the quantum error correcting framework work in that setting as well? Okay, so these are questions that I'd like to ask. So some fixes to this. So I'd like to enlarge the quantum error correcting paradigm to allow for quantum field theory like bulk Hilbert spaces. So now I'm thinking about quantum fields in the bulk. Now, if I have my RT surface, we know that the Hilbert space is no longer going to factorize if I really have quantum field theory, because instead of associating a Hilbert space to this region A, I just should associate a subalgebra, right? So this is the subalgebra NA. It's a subalgebra of all possible operators that act on this Hilbert space. Of course, take it to be a von Neumann algebra, meaning its double commutant is equal to itself. And yeah, so that's one thing that we'd like to build in. The other thing is that now that we're in infinite dimensions, because we have bulk quantum field theory, so we have infinite dimensional Hilbert space, we have to be careful how we treat the sort of the approximate nature of the code. So previously, I sort of motivated using this operator norm to say how good your code is working. However, in general, that won't be sufficient. And instead, we're going to have to use this sort of pointwise approximate, where I'll explain what that means. So instead of talking about some uniformly approximate code, we'll talk about pointwise approximate codes. And another thing that I'm going to build in, which sort of comes out naturally from this, is I'm going to simultaneously incorporate the large n limit in the code. So how do I do that? Well, I imagine I have a sequence of boundary theory Hilbert spaces. I'll call them kappa n. So they come from the sequence of CFTs that I imagine exists in my ADS CFT setup. And H here is just the code. And the interesting thing about the code that I'm going to build is that it's the same for each n, right? So you can, if you like, you can think of it as the infinite n theory, and I'm somehow I'll be embedding the infinite n theory in the finite n theory. Okay, so you get these maps of Vn, which are like these isometry maps before, but now they're just linear maps between the bulk Hilbert space and this boundary Hilbert space, which is the physical Hilbert space at finite. So I have a sequence of these encodings. Now, to motivate the structure, the final structure of this error correcting code, I'm going to prove, or I'll give you, I won't prove it for you, but I'll give you a theorem that we proved, which is a generalization of this theorem that I flashed before. I forgot to mention that that theorem is sometimes called the information disturbance tradeoff theorem. And so I'm going to prove a version of that in this sort of sequence of theory setting. So we're going to firstly assume, so I'll explain what this means in a second, but we're just going to assume that Vn dagger Vn limits to an isometry. So it's not an isometry, it's just a linear map between Hilbert spaces, but it will limit to an isometry. In that context, the following two statements are equivalent. So this is similar to the previous exact case. We have operator reconstruction and some nil Laflamme-like condition. So in this case, the operator reconstruction, we have these maps, these unital completely positive maps. Yeah, sorry. And this theorem pertains to two subalgebras. A sequence of subalgebras on the boundary theory. So this is Mn, which are subalgebras of the boundary region, which you should think of as being representing some subregion on the boundary, and some subalgebra in the bulk theory. So for pertaining to those two things, these two statements are equivalent. So if I have one, that implies two. If I have two, that implies one. But of course, I may have neither. Okay, so the first statement is that I can do this operator reconstruction, which means I have this map between the bulk algebra and the boundary sequence. So I have a sequence of maps between the bulk algebra and the boundary algebras. And they satisfy this condition, which is the operator reconstruction condition, but only in a limiting sense, okay? Yes, they're on the board, but I'll get to it. And then, yeah, I will in a second. And then for all bounded, and so the second condition is this nil-Laflamme condition, where we take the errors live in the commutant of this algebra, and we project them to the code, and they should commute with the bulk algebra in a limiting sense. Okay, so to define these limits, these are pointwise limits, right? So as opposed to uniform limits where I would take the operator norm, in infinite dimensions, there's a different kind of limit you can take, which are these sort of pointwise limits. So this is the weak operator limit, and I've written it here, which is just the statement that I fixed two states in the Hilbert space. Oh, you can't see that? Yeah, I fixed two states in the Hilbert space for good, and then I take the limit as n goes to infinity, and this just approaches one, which would just give me the overlap between those two states. And this works for any two states in the Hilbert space. But I have to fix them. So I'm not allowed to take sequences of such states, okay? I can just have to fix them once and for all, and then take the limit on Vn dagger Vn. So that's the weak operator limit. And then the strong operator limit is the statement that if I act with any state with this operator on any state in the Hilbert space, and then in the Hilbert space sense, this goes to 0, and that's true for all vectors. And again, it's a pointwise limit because I can't do this uniformly. If I did allow for sequences here and here, then I would just get back my uniform statement. Okay, great. So yeah, and good. Okay, so this is a theorem we proved. So it motivates introducing a code where Vn is the sort of the encoding map. Now there's a complementary version as well. So if I assume condition 1 of the previous theorem applies to these two algebras, as well as to the commutant algebras. So this is like this complementary setting where we had complementary recovery, what I should have called when I introduced that. Then if we have both of those, you can show that the relative entropy is asymptotically equal. That means if I take a limit of the relative entropies in the sort of physical associated to the physical algebras, that equals the bulk relative entropy. And this is true for all fixed states in the Hilbert space, in the bulk Hilbert space. And then the final statement, equivalent statement, is that you can also do this for modular flow. So the modular automorphism is some map on the, is some automorphism of the algebras themselves. In the type 1 case, it's just take the density, it's a state-dependent automorphism. In the type 1 case, it's just take the density matrix to the power of IS and conjugate it like this. In the type 3 case, we have to be more careful. We have to introduce these modular operators, and it's just conjugate by these Tomita-Takasaki modular operators, and you're just conjugating by these. And so so if we have this, if the modular automorphism commutes with a code, then you can also prove that you have this sort of operator reconstruction statement for the algebra and its commutant. Okay, good. So now I've flashed this theorem. I will also tell you another statement about this, which is that this kind of map and this kind of quantum error correcting code, we can directly derive up to some assumptions, just by thinking about how you would usually take the large n limit in a matrix-like theory, which is relevant for ADS-CFT. And I think, you know, a quick sketch of the physics that's going on here. So the Hilbert space, the bulk Hilbert space will be built out of single trace fields. At any finite n, these single trace fields, as I mentioned, don't form an algebra. If you act with enough of them, you might create a black hole. And that should be outside of the code that we're trying to describe. However, if I fix some state in this Hilbert space, which again is created by these single trace fields, any number of them, but a fixed number of them, then this state, if I now map it to the physical Hilbert space, this will be a sufficiently good representation of the physics at some sufficiently large n. And that n will depend on the input state psi. And that's why you naturally get these pointwise limits. Okay. What's my time like? Okay. All right, so we can give a little bit more details. I can give a little bit more details about this derivation. And essentially, it's following these recent papers discussing the emergence of non-trivial von Neumann algebras from large n limits. And the idea is to think about single trace fields. As I said, you have some large n, and use the fact that you have large n factorization. So we have some set of single trace fields. We pick a sequence of states that we imagine has a smooth large n limit. And we note that the correlation functions have some nice sort of generalized free form. They're just determined in terms of 2-point functions after I subtract 1-point functions. And so, you know, these operators behave like generalized free fields, at least at infinite n, okay? So based on that, I can consider some abstract algebra built out of the infinite n fields, which you can just think of some label on operators. In fact, this is some abstract C-star algebra. The sequence of states that we needed gives us limits to a state on this C-star algebra. When you have a state and an algebra, you can always construct a Hilbert space using the GNS procedure. So we have a Hilbert space. We also have reconstruction maps, sort of very simple reconstruction maps. These are defined as follows. Just basically take the single trace fields, the representatives of the single trace fields at infinite n, these labels, and write down what is the finite n version of that, right? So that's really what we mean by the single trace operator. We have a representative of that operator in each of the n theories. And so that map is just doing that. And then finally, once you have this map, you can define this Vn encoding in the quantum error correcting code, just using a linear representation of that map. And then modulo some assumptions on the convergence of these correlation functions. You can argue you get these weak operator and strong operator limits. Gamma n here is kind of like the global reconstruction map. Now, one thing that you can also do when you have this is we can incorporate algebraic quantum field theory. In particular, you might want to incorporate the locality of the boundary theory. And the way to do that, of course, is with algebraic quantum field theory. So the boundary theory we take to be this cylinder, as usual. Then associated to causally complete regions on the boundary, we're going to assign a von Neumann algebra, which is a subalgebra. Well, actually, we're going to assign a sequence of von Neumann algebras in the physical theories. And they're subalgebras of all possible operators in this physical theory. Yeah, okay. And this is the standard sort of algebraic quantum field theory setup. There's various consistency conditions on this assignment that I'm not going to talk about, but they're kind of obvious. Now, a thing that's less obvious if I take this causally complete region and I take its causal complement on the boundary. So if I have a boundary diamond, for example, O prime is also a diamond on the cylinder. It's just the complement diamond. In this setting, I can think about the von Neumann algebra assigned to this causal complement. And I have something called Hague duality if it's sort of maximal. So that means it is equal to the commutant of all operators in this boundary region. In general, this is just a subalgebra of this commutant here, just by sort of causality, Einstein causality. But when we have Hague duality, we saturate that. And this is just telling you that you have sort of a sufficiently complete description of the quantum field theory. It's a very natural thing. In particular, it's going to be a natural thing for us at finite n. And then the question will be, does it survive as n goes to infinity? So in this setting of algebraic quantum field theory, we can also localize these simple reconstruction maps, gamma n. In fact, they localize to a subalgebra. Remember, they were acting from the single trace infinite n theories to the finite n theory. The GNS Hilbert space, you can talk about subalgebras of operators that act on that. And in fact, there's a natural subalgebra associated to boundary regions O, which is just generated additively by these single trace fields. And you're also, these simple reconstruction maps sort of restrict nicely to C of O, and they act, and they sort of localize to O. In particular, they map this C of O to Mn of O, right? So Mn of O is the physical operators in this region O. So the three things that I've sort of defined for you eventually define what we call an asymptotically isometric code. There are these this sort of algebraic quantum field theory net of von Neumann algebras that acts in the bulk Hilbert space, this encoding map, and these simple reconstruction maps. We're also going to assume the existence of a common cyclic and separating vector in this Hilbert space. This is a very natural assumption. So now we can try to give an interpretation for this C of O. The information disturbance tradeoff theorem that I sort of showed for you at the beginning of this actually proves this sort of causality statement for a C of O. You know, this is a non-trivial statement, but yeah, we proved it with that theorem. And you know, based on this and various other reasons, C of O you should take as being representing the causal wedge, right? So operators in the bulk quantum field theory that are localized in the causal wedge. Okay, so the causal wedge is just the causal completion of the boundary region O now in the bulk. And for, you know, if we actually have a gravitational dual. And if I just project this to a time slice, typically you're going to see violations of Hague duality. That means if I think about the causal wedge for the boundary region O versus O prime, there's going to be a gap in between. So this Hague duality has been violated in the limit as n goes to infinity. The other thing that sort of identifies this as the causal wedge is that these operators, these gamma n are sort of simple reconstruction operators. And they're constrained by bulk causality. Okay, so then what do we mean by an entanglement wedge? Well, an entanglement wedge is the sort of maximal extension of the causal wedge. So if I take the causal wedge, I can try to extend it further out here, doing some kind of reconstruction maps. These reconstruction maps may or may not exist. If they do exist, there may or may not be a maximal one. That means one where I can do sort of reconstruction in some region E of O, and in the complement region, I can do reconstruction in E of O prime, and these are commutants of each other. That means an entanglement wedge in my language is just a Hague dual extension of these causal wedges. It satisfies all the properties we expect. Now, okay, so now that I've set up what a sort of asymptotically isometric code is, the real big question is, do these entanglement wedges exist? The causal wedges always exist, but can I sort of push them to this entanglement wedge, these Hague dual things? So there is a setting where we can say some things like that, and that is the setting of a vacuum code. So this is new work. So of course, a CFT has conformal symmetry. That's represented as some unitaries acting on the finite n Hilbert spaces. So there's actually a sequence of these unitaries and vacuum states that are left invariant. These unitaries act naturally on the von Neumann algebra. They just sort of covariantly on the von Neumann algebra. Now this code, the code itself may or may not furnish a representation of this symmetry. So what you should think of as here is that I'm sort of in this strict large N limit. So I'm thinking about quantum fields on top of some background spacetime. And if that spacetime doesn't have these symmetries, then the Hilbert space of those fluctuations won't realize that symmetry. So in particular, in this case, in the vacuum code case, I'm thinking about small fluctuations on top of ADS where we have these symmetries. And these symmetries will be realized on this Hilbert space. And in fact, there should be a map between them as n goes to infinity. So these assumptions here are what I mean by a vacuum code. And vacuum codes have some consequences. The first consequence is that for the special boundary diamond regions, which is just sort of the intersection of the past and future of the light cone of 2 points, you can prove that the causal wedge is already maximal. That means that the entanglement wedge equals the causal wedge. This is a kinematical result. It actually just follows from symmetries. It follows from the fact that the modular operator that I talked about before for this sort of diamond region, the raised to the power IS is just the generator of a conformal symmetry, a special conformal boost that holds fixed the diamond, right? And okay, so actually proving this, this was proven in this paper. It's kind of like an algebraic version of Bissig-Nano-Wichmann. It's actually a little bit non-trivial proving this statement. Once you have this statement, it's sort of 2 lines to prove that you have this Haag-Dual property. Okay, but I won't go over the details. Now that's sort of kinematical. That would apply to any kind of code that you could imagine, even a very highly stringy code. There is a more non-trivial consequence. So suppose I have a theory where with the following property. So I can now talk about the partition function of the theory. So if I talk about the partition function of the theory on the cylinder, so H here is the Hamiltonian for time translations on the cylinder. And I take the limit, and if I end up on the bulk partition function, where now this is the generator of time in the bulk, which exists by sort of assumption of these vacuum codes. If this limit is faithful here, then we can show the entanglement wedge is added for 2 diamond regions, disjoint diamond regions, is additive over the causal wedge. And where this is true for sufficiently separated diamonds. And it turns out that the sufficiently separated condition is exactly the condition that this Hawking-Page temperature, of course, this is true below the Hawking-Page temperature. Above, it's violated. But below the Hawking-Page temperature, this is true. And then you can show this is true as long as the 2 causal wedges are separated by more than beta Hawking-Page in the bulk. So there's some minimal geodesic between the distance between these 2 causal wedges. And if this is further than this beta Hawking-Page, then you can prove this property. This is, of course, what we expect. In fact, what we really expect is that for some distance, we expect when the entanglement wedge is just the disjoint union of the 2 causal wedges, then this should be the case. And in fact, this occurs as long as the mutual information, we're away from the mutual information phase transition where the entanglement wedge gets connected like this. Okay, so this happens really somewhere at a distance scale over here, which is separated from this Hawking-Page distance. And so there's a gap, but that gap is just like, we can't prove it. So we've managed to prove that the entanglement wedge is additive. Ooh. Yeah. We managed to prove the entanglement wedge is additive over here. Over here, we haven't proven it. Maybe there's some other methods that let you prove it. Okay, so now where does this come from? Where is this relation between partition functions and diamonds coming from? Well, it comes from something called L2 nuclearity, which is some trace condition. So imagine I have my 2 diamond regions, and I think about their modular operators. If I form the following combination of the modular operators, delta 1 to the -1/4, delta 2 to the -1/4. You can show that this is a bounded operator always. It may or may not be a trace class operator. It turns out that if it's a trace class operator, you can prove the algebras are split. So the algebra being split means that the algebra generated by the two diamonds is the same as the tensor product or isomorphic to the tensor product algebra. This is a non-trivial statement. You can see why it might be non-trivial if I take the two diamonds just to be a diamond and its causal complement diamond. In this case, we have type 3 von Neumann algebras, and we know there's no factorization like this. It turns out it's even non-trivial when the diamonds are separated. And it relies on, well, one way to prove it is with the finiteness of the trace of this operator. And of course, now it turns out that conformal symmetries allow you to compute what this operator is. And it's just the partition function. It's just e to the minus beta h, where beta is then has the interpretation as the geodesic distance between these bulk causal regions. That's just some coincidence. I haven't said anything about ADS CFT at this point. In fact, this was all for fixed n. Okay, so now in the case where we have this sort of limiting statement, we take a limit of these modular operators and we get the bulk modular operators. You can use this statement to prove, well, that the split property commutes with the code in a certain sense. So it's in the following sense. If I take the split state, so the split state always exists if we have the split property. It's just a state that lives in this Hilbert space that when you restrict to this von Neumann algebra is completely factorized, okay? So it's non-trivial that that state exists, but it's represented by some vector. If that sequence of vectors commutes with the vector in the corresponding vector in the code subspace, then yeah, so you can use this property to prove this, and then this proves that the entanglement wedge factorizes. This is perhaps not so surprising because the split state means that you can, yeah, everything sort of factorizes naturally. Okay, now there's another region in this diagram that I sort of delineated over here, which is related to a Hagedorn transition. So what do I mean by that? Well, if I just think about the bulk partition function, the bulk partition function, this guy here may or may not agree with this limit. So above the Hawking page temperature, if I take a limit of the boundary theory partition functions, I'll get infinite. The answer is infinite. But the bulk partition function will still be well defined. I'll still be able to compute it. However, there is another point below which the bulk partition function may just not be defined. And that's related to Hagedorn divergences. So in particular, if I actually had a string theory in the bulk, the density of states grows exponentially. And so that means if you try to compute this partition function above some temperature, which is this Hagedorn temperature, you get the answer is infinite. So, you know, that's the setting where the causal wedges are very close to each other like this. They're within a string length of each other. And in that case, this sort of nuclearity condition goes away. So you don't have this bulk nuclearity condition, which means it's possible that we lose the split property. I don't know for sure that we lose the split property, okay, because it's not an if and only if statement. Okay, so one thing you can do now is you can do this for more general diamond regions. What I was just talking about, I didn't mention it, was for two diamond regions that are on the same time slice. If you do two diamond regions that are not on the same time slice, you can compute the same modular operators, and you find correction which comes from the angular momentum for rotations on the sphere. Just pick one of the rotations, it doesn't matter. And you get this relation between these modular operators and this partition function. So this, in particular, you know, I can map out the space of these disjoint diamonds by thinking about the 4 points here and constructing two conformal cross ratios related to the 4 tips of the diamonds. And now I get a phase space that lives in this sort of, in this square here. The fixed time slice case is just z is equal to z bar. more generally, I can map out this space with the diamonds, and in particular, there's corresponding temperatures given by this relation here. So then in this picture, I can sort of fill out what might happen to the Hawking-Page transition, the mutual information phase transition, and the Hagedorn transition. I'm almost done. In this region, just to explain, in this region, we have a proof that the entanglement wedge is additive. For this, here, we expect it to be additive. We do not have a proof. And over here, mod L2 nuclearity in the bulk breaks down, which may or may not mean that the bulk algebras are split. Okay, so let me just finish with my conclusions. We've constructed quantum error-correcting codes that are capable of capturing features such as quantum field theory Hilbert spaces, dynamics, causality, and locality. In special cases, in particular these vacuum codes, we could prove statements about the existence of entanglement wedges, which are non-trivial. Very likely, if we want to impose some condition that our code should have a local bulk, we should at the very least require this sort of L2 modular nuclearity. Perhaps we should just require the split property for all pairs of space-like separated causal wedges. And this has some nice string theory interpretation. In particular, if we did impose this, then it suggests that it's not a string theory. Okay, so there's future work. This is just an example of a code that we can study, these vacuum codes. We could also study thermal codes, try to prove some entropy formula like this, where the type 2 entropy that people have been talking about recently is a limit of type 1 entropies. And then there's a very big and open question, which is how much can you prove about Hague duality or the existence of entanglement wedges beyond vacuum codes? Okay, finish there.
This issue of Hague duality beyond the vacuum and in higher orders. I mean, aren't you eventually going to have to one-shotify all of this? I mean, usually there's this issue of no man's land and so on. And
I'm not sure about that. We're taking very strict large n limits, and it's possible that that's something that we just get rid of. That's one possibility. The other possibility is, we have to, so the two causal wedges, maybe there are examples of codes where the two causal wedges, there's no such thing as an entanglement wedge. And to define that, we might need to, be more careful with what we mean by that.
Intersection of all the entanglement wedges is a sort of minimal entanglement.
Yeah, that's this reconstruction,
Than the causal wedge.
That's right, that's fine, that's fine. Yeah, they don't quite touch. Yeah, that's fine. That's possible. I think there are many interesting situations where that doesn't happen, and so but yeah.
Is there a way to add a derivative model interaction to this?
I think so. We haven't done it. All of our statements were limiting statements, so we don't tell you what the corrections to these are. They could be 1 over log n or something ridiculous like that. What's that? No, I think they're like, but I mean, it's, if it was, it would still be okay with what we've proven. So yeah, but it's a very interesting thing to do that.
Is there a sense of what the code subspace would look like if you wanted to include higher trace operators in the larger algebra?
The higher trace operators are there. Like that. When I talk about a single trace, I should have said that single trace algebra means single trace plus multi-trace and stuff. Yeah.
Not excluding any multi-trace operators when you define this general.
No. They're there. Yeah. I mean, it's an algebra, so I have to be able to act with multiple things there. Yeah.
Do you have some intuition for why you only need the weak limit there rather than the strong limit?
No. In fact, it's very light. It's plausible that we should impose the strong limit there. It's just this is what we could prove. So this was the weakest thing yeah, so we could prove it with this, which implies it in the strong operator case. But there might be some other things where it's important that it's the strong operator limit. So I'm not committed to that. It's just some pointwise limit I think is important.
Operator norm.
Yeah, that's the point. It's not the operator norm. Yeah.
If I understood correctly, your causal wedge has a nice reconstruction interpretation, but do you have one for your entanglement wedge? Algebraically defined, but not defined, is that right?
No, it's reconstruction defined. I mean, you can define it like so. So for example, you can do modular flow, and you can prove that the modular flow of the simple reconstruction is sufficient to actually do general reconstruction. So you can prove that statement, yeah.
So Pointwise had this result where we were able to prove that the entanglement wedge is connected to subregions if and only if the algebra type of the canonical purification was type 3. If you take the right reduction of the state. So it seems to me that it's maybe related to the split property here, where the state that you're talking about is the canonical purification. Have you thought about that?
A little bit. Yeah, what can I say about that? Let's see. Yeah, so one thing that you can, when you have the split, another way to talk about the split is, you know, yeah, another way to talk about the split is to think about Mn delta 1 as being a subalgebra of Mn delta 2 prime. And if it's split, you can find a type 1 factor in between. Yeah, there's the split factor. And I think the difference between where you are in this sort of phase diagram is whether that will, in the limit, will be a type 1 factor or will be a type 2 or type 3 factor. Yeah, probably a type 3. Yeah, it'll probably be type 3 for the vacuum. Yeah, yeah. And so yeah, if you think about, we haven't really thought much about that type 1 algebra, but yeah, what becomes of that is the interesting question there. Yeah.
So, can you please comment on the fact that, for you at every finite n, you have a subalgebra? So, but in finite G Newton, or like, we don't think we're dealing with subalgebras. So if you have any comments about that?
Well, you know, we do if we talk about the CFT, right? So that's the thing that's anchoring thing. We have a really well-defined concrete theory on the boundary, which I'm giving myself. You know, maybe you're not happy with that, but yeah. So we have a well-defined. I'm imagining we have a well-defined CFT at finite n, and then we have nice algebras. Yeah, well, I guess it depends what you mean. Yeah, but I'm not talking about single trace. I'm talking about all operators, not single trace operators. When I say, yeah, everything, like Wilson lines, everything.
Just wondering, do you think there could be a general result relating L2 nuclearity to, well, modular nuclearity to chaos of modular flow or something like that?
I think you should ask Nima about that. Yes.
States?
It does not. Yeah, so it depends on the subspace. So it's subspace dependent, but it's not state dependent in the subspace. Yeah.
If you had a tie, then it would be. If you this thing of having a tie.
Yeah, so there's an interesting question about what happens in this very limiting sense. If your regions are exactly on a phase transition, then yeah, I don't exactly know that what happens then.
It seems like I would want to include the ability to change.
Yeah, so I think it's a different sector of the theory when you do that. So it's impossible when you do that, you just naturally have Hague dual violations. And that's not inconsistent with anything that I said, yeah.
You have one shot.
Yeah, then you might be one to one shot, yeah. That's right. Yeah, I think it's also possible that some of those things go away when you take the strict large n limit. So it sort of depends on it may depend on the state that you're actually working in, whether you include certain fluctuations or not. Yeah.